Then do you have a specific section you need help with from the MyLab Math assignments? Specific questions there or from the review? Okay, all right. So then I plan today, half the time we cover some questions from 3.7. The other 25 minutes we cover some questions from section 3.8. Let's get started. 3.7. Arguments and truth tables. Be sure to watch the video and study the content before you working on your homework. Fill in each blank so that the resulting statement is true. The argument, the first premise is P implies Q. Second statement is not Q. Therefore, is called contrapositive reasoning, and it is true because it is a tautology, so not P. All right, let me get the notes. If we have a statement, conditional statement, with antecedent P, consequent Q, and its contrapositive is also a conditional statement with antecedent not Q, consequence not P. Yeah, those two statements, they are contrapositive of each other. When two statements are contrapositive of each other, they always are true, both true or both false, or equivalent. They are equivalent. So they always have the same truth values. And this reasoning is called contrapositive reasoning. From P, if P then Q, now not Q occurs, then we have the consequent not P. This is called a contrapositive reasoning, and it is always true, is valid. Yeah, the argument is valid because the equivalent conditional statement would be this one. As you can see, the first premise, P implies Q, and second premise, not Q, is the antecedent, will give us the consequent. Yeah, this statement, conditional, is a tautology, means in all cases it is true. Yeah, that is about contrapositive reasoning. Number 2, fill in the blank so that the resulting statement is true. The fallacy of the inverse has the form P implies Q and not P, so not Q. This is a fallacy. Okay, let me explain the definition. Inverse. For the statement P implies Q, its inverse is not P implies not Q. Those two statements are not equivalent. In my video, I have this example. It is raining. Q is the grass is wet. The grass is on the outside. If it's raining, of course, the grass will get wet, right? Yeah. So the statement, a given statement is true. However, its inverse not necessarily is true. The inverse can be translated as if it's not raining, then the grass is not wet or is dry. Well, when it's not raining, the grass could be wet for many other reasons, right? You could manually water your grass. So P implies Q and its inverse are not equivalent. In general, they do not have the same truth values. So this is a fallacy. It's called a fallacy of inverse. Number 3, determine whether the statement below is true or false. If the statement is false, make the necessary change or changes to produce a true statement. Let's read the statement. The conclusion of a sound argument is true relative to the premises, but it is also true as a separate statement removed from the premises. Let's see. I think this is not true. This is false. If we change the conclusion as premises, that would be sound. Yeah, change conclusion to make this statement true, change conclusion to logic. The logic of a sound argument is true relative to the premises, but it is also true as a separate statement removed from the premises. To make this statement true, change also true to not true. An argument is valid if the conclusion can be drawn from the premises logically. But valid argument may not necessarily be sound. In order for a valid statement to be sound, all the premises has to be true. All the premises have to be true. To make this statement true, change, removed from the premises. Let me try this one. If not, we try A. Nope. This statement is true. Oh, okay. Recall that the soundness of an argument is based on its logical validity, not the validity of the premises. Okay, so yeah, let's look at question number 3 one more time. The conclusion of a sound argument is true relative to the premises, but it is also true as a separate statement removed from the premises. This statement is true. Conclusion of sound argument is true. This statement is true. Recall that the soundness of an argument is based on its logical validity, not the validity of the premises. This is different from what I knew. What I knew is valid argument may not sound. In order for a valid statement to be sound, all the premises have to be true. Okay, just remember this question, number 3. This statement is true. Question number 4. First premise, not P implies Q. Second premise, P. So not Q. So this is a fallacy. Fallacy of inverse. We had that covered in question 2, right? Yeah. Oh, hold on. No. So yeah, it is. It is fallacy of inverse. So P is the negation of not P. Not Q is the negation of Q. So this is invalid. Again, it's a fallacy of inverse. Number 5, use a truth table to determine if the following symbolic form of an argument is valid or invalid. Not P implies Q. Now we have not Q, so we have a P. You know, we don't have to use truth table. We could use the contrapositive reasoning to determine this argument is valid. Okay? The first premise has antecedent not P, consequent Q. And the second premise is the negation of the consequent. And the conclusion is the negation of the antecedent. That is a contrapositive. That is called a contrapositive reasoning. Is always valid. Determine whether the argument is valid or invalid. Compare the argument to a standard form or use a truth table. First premise, P or not Q. Second premise, Q. Conclusion, not P. Is the argument valid or invalid? Q occur. Well, let's try the truth table here. My feeling is invalid, but let's do not rush on that. Should not take too much time to get a table for that argument. Translate with the equivalent conditional statement first. Okay, we have Ashley and then Natalia join us. Now let's translate. So this can be translated as a conditional with the conclusion as consequent, not P. And the antecedent has two parts, so it's a conjunction. The first piece is P or not Q. Second piece is Q, right? So let's make a table for that. One, two, three, 4. PQ, TT, TF, FT, FF. And the last column is my target. Okay, is my target. And this column is going to be the consequent, not P. Not P. And this column, I'm going to have my antecedent. First piece, P or not Q. Second piece, Q, right? And this is going to be Q. I don't mind to copy one more time. And this is not Q. And this one is P or not Q. All right, let's fill in the blank. To negate the Q, we have F, T, F, T. P or not Q. So column 1 and column 3. 1 or 3. Yeah, P or not Q. The disjunction of column 1 and column 3. For the disjunction to be false, only one case is false. All other is T. Yeah, as long as you see one true, and that is true. Only in this case, third case, both of the two components are false, so the disjunction is false as well. And let's copy Q, TF, 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 TF. And this column is the conjunction. 1, 2, 3, 4, 5, 6. 6 is 4 and 5. It's a conjunction of 4 and 5, the preceding two columns. Conjunction. For a conjunction to be true, both of them have to be true. So if you have one F, the conjunction is F, not P. Let's negate the column 1. We have F, F, T, T. Now we are ready for the target. The target has 6 as antecedent, 7 as consequent. Let's look for trust the friends forever. Trust the friends forever. Otherwise, it's temporary, temporary, temporary. Okay? So this is Let me double check. F, P, or not Q. Q. So this is true. Not P is false. Trust the friends forever. So this is not tautology, is not valid, invalid. In the first case, the validity does not hold. Yeah. So I proved, use the truth table proved. It is invalid. Use a truth table to determine whether the symbolic form of the argument valid or invalid. P implies Q, Q implies P. So P and Q. Well, let's use a truth table. This section is a good practice of a truth table, application of truth table. Translate conditional with consequence P and Q. And the antecedent has two pieces, two premises. First premise, P implies Q. Second premise, Q implies P. Be careful because sometimes, I feel sometimes the P and the Q looks very similar. If you're not careful, you might look at it wrong. First piece, P implies Q. Second piece, Q implies P. Let's do the table. 1, 2, 3, 4. P, Q. T, 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 F. F, T, F, F. And last column is the target. I'll just use the star. Yeah. And this column is going to be the consequent. And this column going to be the antecedent. P implies Q. Q implies P. That could only say that P and Q are equivalent. It does not necessarily say P and Q. Well, we'll see. We'll see if it's sometimes it's against your instinct. So we have to be very cautious, be careful. And this one is P implies Q. This is Q implies P. So I have column 1, 2, 3, 4, 5, 6, and 7. P implies Q. Remember, trust the friends forever. All other temporary. Q implies P. Be very careful. Q is the antecedent. P is the consequence. So trust the friends forever is in case 3. Yeah, with true antecedent, false consequent. Trust the friends forever. And all other cases are true, or temporary. Number 5 is the conjunction of 3 and 4. Number 5 is a conjunction of 3 and 4. So for the conjunction to be true, both of them have to be true. So this is true, this is true, and this is a false, this is false. And C is the conjunction, column 6 is the conjunction of 1 and 2. Don't look at it wrong. For column C, you have to look at the column 1 and 2. For column 5, you look at the 3 and 4. So for that conjunction to be true, only this is true. All other are false. Okay, now number 7. Number 7 is 5 implies 6. Is a conditional. It's a conditional. So we are looking for trusted friends forever. Trusted friends forever. And all other temporary. Yeah, we do have a case that will make the argument equivalent conditional statement false. So this is invalid again. Invalid. Use a truth table to determine whether the symbolic form of the argument valid or invalid is right here. R implies Q. Q implies P. So P implies R. That's definitely invalid. Okay? Based on the two premises, we could only have the conclusion that R implies P, not the converse. Not the converse. This is, let me see if I can find a guided notes. This is section 8. Not 3.7, right? 3.7. Right here. There's a table in that section. That fallacy is one part of the table. Right here. Yeah, misuse. Okay. So P implies R. Yeah, P, let me move this a little bit. Yeah. P implies Q, Q implies R. Does not give us R implies P. This is the misuse of transitive reasoning. If you be aware of those fallacies and reasonings, we don't have to use the truth table, right? Yeah, very obviously this is invalid, is a fallacy or misuse of the transitive reasoning. Let's do one more and then we move to the next section. Translate each argument into symbolic form, then determine whether the argument is valid or invalid. You may use a truth table or, if applicable, yeah, they give you this table that I just shown you from the guided notes, right? Yeah. Okay. Let's look at the argument. If he plays sports, he will not play with us. Second premise, he will play with us. He will play with us. He does not play sports. So the argument is valid. The symbolic form of the argument is P is the statement he plays sport. So P implies, let me make a parenthesis. He plays sport is P. Q is he will play with us. If then, right? If then, yeah. If he plays sports, he will not play with us. Q is he play with us. So that is not Q. Q is he will not play with us. So he will not play with us would be not Q. That in second one, he will play with us. The argument. How do I do argument? Argument has 3 lines, symbolic form. I guess we have to translate it to the conditional. Second piece premise is he will play with us. He play with us would be Q, right? And the conclusion would be he does not play sports. Not P. Not P, sorry, not P. This is a contrapositive reasoning. Contrapositive reasoning. Let me double check. Sorry about that. Yeah, this is my personal device. It's not perfect. I think it has a virus. Constantly has the advertisements popped out. P implies not Q. Now it's Q, so we have not P. This is a contrapositive. Okay. All right, we covered 9 questions from section 3.7. Yeah, very important. If you are given an argument, how do you translate the argument to its equivalent conditional statement and set up a truth table or use the reasoning to determine the validity of the argument, valid or invalid. So now let's go to the next section, 3.8. Argument and Euler diagrams. Section 3.7, we use truth table as the tool to test the validity of an argument. Section 3.8, we have a new tool. It's called Euler diagram. Euler diagram. And we use this tool to determine the validity of an argument if the premises of the argument are quantified statements. Yeah, you might remember, what is quantified statements? Quantified statements have the word all, no, none, some, yeah, something like that. Okay, let's get started. Fill in the blank such that the resulting statement is true. The figure below illustrates the quantified statement. Some A are B. Some A are B, right? Because it's stressing the dot. The dot is in a common region of A and B. That means some A also belong to B. Yeah, so some A are B. In total, we have four types of quantified statement. I need you please remember or know their corresponding Euler diagrams. Let me get guided notes. Guided notes are very important. It is the shorter version of our textbook. It's not that I do not recommend that you read a book. Of course, if you have the time to read a whole book, it's good. You're going to learn a lot of stuff. But if you have the time, you should go over the content in the guided notes, because the guided notes is the shorter version of textbook. If you understand the content in the guided notes, you pretty much know almost everything from that is required by the course. So those are the 4 types of quantified statements and their Euler diagram. Yeah, earlier we had the bottom left. The one we had earlier is the bottom left. Okay, so question number 2. Determine whether the statement is true or false. If the statement is false, make a necessary change to produce a true statement. Truth tables are used to represent quantified statements.
The statement is false.
Is a false, yeah. To make this statement true, we change the truth table as a Euler diagram, right?
Yes.
B. Very good. Is the tool for second tool we can apply to test the validity of argument if the quantified statements are the premises. Very good. Question number 3. Use Euler diagrams to determine whether the following argument is valid or invalid. Number 1, premise 1. All silverware is dishwasher safe. Premise 2, all forks are silverware. Conclusion, so all forks are dishwasher safe. Yeah, it's actually valid. Let me show you why. Yeah, that one is pretty consistent with our instinct. Yeah, so this is forks. Forks, F-O-R, and this is a silverware, W-A-R-E, and the bigger circle is things that the dishwasher safe. Dishwasher safe. All right, yeah. So the first premise says, let me go back. First, let me close this one. 3.8 is right here. Yeah. First premise, silverware. All silverware are some things dishwasher safe. So that's how do we have the second circle is inside the biggest circle. And second premise says all forks are silverware. And that's how we have the smallest circle is inside the second circle. Yeah, all forks are silverware. So our conclusion, all forks are dishwasher safe because the smallest circle is also completely fall inside the biggest circle. Yeah, this is a very straightforward argument. We can use Euler diagram to test the validity very easily. This one, first premise, all pythons have forked tongues. Second premise, all snakes have forked tongues. Conclusion, all pythons are snakes. That might be a problem.
Invalid.
Yeah, so we need to find one graph that would not give us the conclusion. So this is the biggest circle is things with what is that? Tongues. Yeah, tongues. T-O-N, tongues. Okay. Let's use this small circle to represent pythons. And this is snakes. Yeah, let's double check. All pythons are things with forked tongues. Yeah, not just tongues, forked tongues. Forked tongues. And all snakes have forked tongues. Therefore, all pythons are snakes. Definitely invalid. Yeah, because the smaller circle, the two smaller circle could be disjoint, like what I draw here, or they could overlap, right? Yeah, they are not necessarily have pythons completely inside the snakes. Do you see that? Yeah, this is just one case, but this case or disjoint case shows that the conclusion not necessarily always be derived from the premises. So that is definitely invalid. Question number 5. First premise, all rocks are hard. Second premise, no marshmallows are hard. Therefore, no marshmallows are rocks. So we have 3 categories here. Rocks, things hard, marshmallow. Okay. Rocks, things are hard, that are hard, or hard things. Yeah, the first premise says all rocks are hard. Okay, that's the diagram for the first premise. Second premise, no marshmallows are hard. So that means, let's say this is a marshmallow. That means the set of things are hard and the set of marshmallow are disjoint. They do not overlap, right? Yeah. So can we make the conclusion that no marshmallows are rocks? No marshmallows are, yes. The two small circles definitely are disjoint as well. Yeah. If the bigger circle and the marshmallow are disjoint, then the smaller circle rocks, which is inside the bigger circle, and the marshmallow, of course, are disjoint as well. Yeah, they do not touch, they do not overlap, they do not have any common members. This is valid. Question number 6. First premise, all rocks are hard. Second premise, no sponges are rocks. Therefore, no sponges are hard. Okay, so this might be, I think it's invalid, but let's see. So 3 things again, rocks, things are hard, and sponges. Okay, let's see. Messages. Carly, thank you for coming. Oh, sorry about the crisis. Appreciate that you are attending the class. Yeah, I know this is a difficult time. Just know that there's no punishment from if you're missing work due to the outage, the power outage. If you need an extension, I can always give you extension. All right, no problem on that at all. So let me write down the attendant student today, Ashley. How are you feeling, Ashley, today? Natalia and Leia. Yeah. So if you have electricity, if you have the conditions to study, please prepare very well, get ready for test 1 next week. Very, very important. In total, we only have 3 tests. Yeah. So each test is so important for your final grade. Okay, so what is the problem? I have to look at it again, I forgot. Rocks, hard, sponges, no sponges are rocks. Okay, so rocks, all rocks are hard. Yeah, hard things. That's the first premise. Second premise, no sponges are rocks. No sponges are rocks. That could only say that sponges and rocks are disjoint. Yeah, the small black circle and the blue circle, they are disjoint. Can we derive the conclusion that no sponges are hard? No. As you can see, it might overlap, right? Yeah, we cannot derive that conclusion, so it's invalid. Invalid. And let's go back here. Natalia, I'm still without power, but I charged the laptop and the hotspot box at work. I have a few questions. Can we walk in, take the test? Can we walk in to take the test?
Yes.
I think you could, but I would recommend you call the testing center. For example,
to make an appointment.
Yeah, not making an appointment, to ask the hours, just in case. For example, you get off work 5 o'clock, and you do not assume the testing center close at 6. You have to call them to ask them, when do you close, right? If they close at 5, you wanna at least get there at 3. You see what I'm talking about? So it's always good to call. Yeah.
Okay.
Yeah. Are we able to still pass the homework for points? Yeah. My intention is all the homework due the end of the semester. The reason I didn't set them as the last day, because if I did that, some of the students really would wait the last week or last few days to work on the assignments, and it's not possible for them to get that done. So to keep you on track, not fall behind, I have the due day set up. But my intention is be flexible. Okay, be
Yes, ma'am.
flexible. If you need extension, just email me. I'll give you the extension. No problem at all. Yeah, that's the second question.
Okay, I'm sorry. Just one more question. These
Mhm.
worksheets, do all of these worksheets need to be turned in, or do they just need to
Yeah,
be done?
no, only four worksheet assignments. So the first one is order of operations, right? The second one is the truth table, is in Blackboard. The third one is the percent, fraction, decimal conversion. And the last one is going to be about fraction. When we get closer to the chapter talking about probability, we deal with fractions a lot. And we're going to assign that the last worksheet assignment. Not all of them that I posted. But if you would like to work on them, I would agree it. But it's not required. It's not mandatory. Only four worksheet assignments are mandatory, means they matter to your score of the essential class. Okay.
Okay.
Yeah,
Okay.
thank
Sorry.
you,
Thank you.
Talia, for the questions. Yeah. So let's go back. So we choose invalid because we see a counter example, right? Yeah. The key of Euler diagram method is to use the diagram to try to find a counter example. If we fail to find any counter example, then it's valid. If we can derive a counter example like this one, rocks and sponges, hard things and sponges, they are not necessarily disjoint, then that is a counter example. That means the argument is invalid. Question number 7. All evergreens are trees. Some trees are maples. Therefore, some evergreens are maples. Yeah, again, do not worry about the sentence itself. You would say, no, not all evergreens are trees, right? Could be bushes. We do not do that. We only care about the logic. That's why we do not consider soundness. For being sound to be a sound argument, it has to be valid at the first place, and all the premises have to be true. Okay, evergreens, trees, maples. Okay, all evergreens are trees. So evergreens are trees. That's the first premise. Second premise, some trees are maples. Some trees are maples. Yeah, some trees are maples. For example, this tree is a maple tree. Can we make the conclusion that some evergreens are maples? No. Yeah. If I draw this, if I make this circle bigger, like the maple circle like this way, then some evergreens are maples. But as you can see, the graph I'm having right now is a counter example. We cannot derive that conclusion directly from the two premises. Invalid. Question number 8. All factors of 6 are factors of 42. Some factors of 6 are factors of 7. So factors of 6 factors of 42, and factors of 7. So let's do 6 and 42. Factors of 6 are factors of 42. Double check. All factors of 6 are factors of 42. Yeah. Second premise, some factor of 6 are factor of 7. Factors of 7. Factors of 7. Factors. Okay, I'm not going to draw this small. I'm going to draw it bigger. This factors of 7. The blue one is factors of 7. So some factor of 6 are factor of 7. It doesn't make it, it's for example 1, right? So you know what? Do not worry about the meaning. Do not worry about true or false of those statements. Some factors of 6 are factor of 7. So that's the smaller black circle and the blue circle, they overlap. Yeah. Can we derive this conclusion? Some factors of 42 are factors of 7. Some factors of 42 are factors of 7. Yes. Hold on. Some factors of 42 are factors of 7. What if this blue circle is smaller? Like that. Some factors of 42. Then they are not overlap. They have a, like all factors of 7 are factors of 42. I would say this is invalid. Let me see. All factors of 6 are factors of 42. Some factors of 6 are factors of 7. Can we say some factors of 42 are factors of 7? Some. No. Because the two different type of quantified statement. Sorry. Your answer is invalid. The correct answer is valid. Some factors of 42 are factors of 7. Some factors
of 6 are factors of 7. Yeah, I think it's valid. Yep.
If like that is true, is valid. If the blue circle is smaller, we still have overlapping part. Okay, it is valid. Let's do a similar problem. All factors, okay. So all factors of 6 are factor of 42. Some factor of 6 are factor of 7. Some factor of 42 are, isn't that the same thing? So it's valid. Okay. Do one more. All English professors are good readers. J.R.R. Tolkien. JRRT is one of the English professors. Therefore, JRRT is one of the good readers. That's definitely valid. Yeah. So this one is straightforward. English professor. Good readers. So this dot represents the person. The person is an English professor, so the person is a good reader. Yeah. All right, so we completed 9 questions from each section, the last two sections of chapter 3. I would strongly recommend you catch up if it's possible for you. No pressure, okay? No pressure, because I know it's a difficult time for everybody. Try your best. Feel free to email me, ask the instructor if you have any questions. I'm almost caught up. Really appreciate. Okay, you're welcome, Ashley. All right, so this is today. I'll see you tomorrow, guys. Yeah, feel free to email me. Have a good evening. Bye bye. You're welcome, Lan. See you tomorrow.